our PhD. So I'm very much thankful to CURaj for facilitating us with comfortable environment when we moved along with our guide, Professor Arun K. Pujari. So I'm humbling to have an opportunity to be part of this FDP and exciting because it is on deep learning. So let me share you the screen first, then we'll start the session. Thank you very much. Is that visible?
Yes.
Am I audible clearly?
Yeah. Yes. You are audible and a screen are visible.
Yeah, thanks a lot. In this session, we'll focus on introduction to deep learning and neural network basics. So this is the overview of my talk. I'll start with the differences between the artificial intelligence, machine learning, and deep learning. Then I'll provide a brief introduction to the deep learning and applications of deep learning. Then we'll more focus on the neural network basics that are required for the rest of the sections. Like we'll start with machine learning basics, things that are essential to cover for the next sections, like gradient descent, regularization. We'll discuss what are shallow neural networks, what are deep neural networks. We also discuss the core concepts of these neural networks, like forward propagation and backward propagation. If time permits, we'll also look at the implementation part of it. So what is the difference between the artificial intelligence, machine learning, and deep learning? So the AI bunch has created much awareness about the deep learning, right? Nowadays, everyone is talking about the deep learning. Okay, a lot of words about this word. I'm sure you are aware of this, though you are not fully aware of it. You must have heard about it, isn't it? So deep learning has created enough bunch of it, isn't it? So artificial intelligence was initiated with an intuition of creating human-like intelligence, isn't it? So when it was initiated with an intuition of creating human-like intelligence to develop programs or to perform tasks that typically requires human intelligence, isn't it? So one of the aspects of human intelligence is that we have the ability to learn things on our own from the experience, correct? So we have the ability to learn things from our experiences, isn't it? So this aspect of the human intelligence is captured in the artificial intelligence through machine learning. So machine learning is a set of algorithms that has the ability to learn without being explicitly programmed. So you need not explicitly program that those who purchase, explicitly program to recommend wireless keyboard and mouse to those who have purchased laptops or systems. Okay, you need not explicitly say that if it has 4 legs and if it has 4 legs, it is animal. And you need not explicitly say this. From the experience, algorithms are able to learn all these rules and classify and learn the tasks, isn't it? So that is one aspect of artificial intelligence, that is machine learning. So then what is deep learning? Deep learning is a subset of machine learning which employs neural networks to learn from the vast amount of data. Okay, so with this brief differentiation between the artificial intelligence, machine learning, and deep learning, you should see each one is the subset of the other. Machine learning is a subset of artificial intelligence, deep learning is a subset of machine learning. Okay, we'll also see that what is the main difference between the traditional machine learning algorithms and the deep learning algorithms. If you observe in any traditional machine learning or pattern recognition models, they work on the handcrafted features. You have to explicitly extract the features from the given data, and they apply relatively simple transable classifiers. See, for example, if you give some image, it explicitly extracts some features which is in the form of vector, and this vector is passed as an input to this classifier or some regression model, isn't it? Any machine learning model for that matters. So it has to explicitly explicitly compute or determine these features. Okay, it's not inbuilt in case of machine learning algorithms. So what are the limitations with this? It is very tedious and costly to develop handcrafted features, isn't it? And the handcrafted features are usually highly dependent on the one application, and we are not sure whether these features are sufficient for the learning process or not. This is also we are not sure. So it is very tedious process in case of machine learning algorithms. So deep learning, in case of deep learning has an inbuilt automatic multi-stage feature learning process. Okay, so the feature extraction in case of deep learning is inbuilt. You need not explicitly extract the features in case of deep learning. And it learns a rich hierarchy of representation. For example, if I want to classify an image as an outdoor or indoor image, you may have different levels of feature extraction. Different modules represent these input data to its higher level as it proceeds deeper through the network. So for example, initial stage, you may have pixels, edges, and then you may have some decorative items, and then you may have parts of the image, and all these different things together able to identify whether it is outdoor or indoor image. So from low level features to mid level features to high level features, all these are learned automatically in case of deep learning. Okay. All right. So if you take an image, image can be represented initially as a set of pixels. From this, low-level features could be edges and texture. Mid-level features to be motifs, some decorative items, or parts. High-level features are the objects. Similarly, if you take some text, a very low level input may be characters, low level features could be words, word groups, mid level features to be classes, high level features to be sentences. All these are required, right? See, when you are detecting humans, when you detect some object, how do you say that whether it is a bird or animal? How do you say that? If it has wings and 2 legs, then you'll classify it as a bird. If it has 4 legs, you may classify it as, isn't it? So for that, you have to identify in a picture whether it has the 2 legs or 4 legs, or it has wings or not. All these things you have to identify, correct? So these high level features, that whatever that we are talking now, either wings or legs, whatever, these are identified through these high level features in case of deep learning automatically. Okay, so each module in deep learning transforms its input representation into high-level one in a way similar to human cortex. That is what the similar thing happens in the human cortex. All right, so that is how we also learn. That is how deep learning is also learning. All right. Similarly, if you want to recognize a face, how do you recognize a face? Initially, it may be pixels, then it may be a set of edges, maybe then parts of a face, then the whole face together, isn't it? So from low-level pixels to high-level face recognition, you have all the different stages in the deep learning that are all done automatically in case of deep learning. Whereas if you take machine learning, all these features you have to explicitly extract from the image. Few applications of this is automatic colorization of black and white images. If you give black and white image, it will convert into color image. Similarly, black and white videos to color videos. Optimizing images like post-processing and feature optimization. You can optimize features like color curves and details. You can optimize features like illumination. You can optimize features like color tone, isn't it? So these are all the different applications of deep learning. Captioning an image, given an image, you should be able, the deep learning is able to give the caption for that image. For example, you can see the first figure, that is a person riding a motorcycle on a dirt road. Similarly, object detection in the photographs, given an image, it is able to detect objects. You can see there are 3 objects in that: person, horse, and dog. Prediction of a next word, given a set of words. You might have seen this in Google also, right? When you are typing something, next word, it will be predicted, right? That is the technology behind that is deep learning. Similarly, automatic converting converting from one language to another language. So all these are the few applications of deep learning. There are many more applications which are difficult to list out. All it is difficult to list out all the applications in this. There are so many applications. Almost in every domain, deep learning applications are there. This concept of neural network is there since 1960. Okay, but since 1980, the form of the models in the neural networks has not changed much. But a lot of tricks, new tricks has been added, but it's not changed much. But the question is now, why is everyone talking about deep learning now? If it is there from 1960 onwards, why everyone is talking about that now? Okay, because now we have got faster computers, CPUs and GPUs. Earlier we don't have, so we were not in a position to handle these complex models using the computers that we had, and new nonlinear functions have been added to the networks that made the some improvement in the performance, and we have some better optimizations now. We are adding more hidden units now. And most importantly, deep learning has won many numerous pattern recognition competitions. Many pattern recognition competitions deep learning has won. It means that it is doing very well on the various problems. And it requires minimal feature engineering, unlike in case of machine learning. Okay, so it is easy to adapt as compared to the machine learning problem, because then you have to do feature engineering and all, and people from different domains may not be able to do it so. And whereas the deep learning, it is directly, you can give the raw data to, you can feed the raw data to the deep learning framework, and you can expect the output with the proper training. All right. And lot of money has been invested in this deep learning. Like Google has DeepMind acquired by Google for $400 million, and DNN Research, the 3-person startup acquired by Google for unknown price tag, and various other startups also acquired. I mean, a lot of money has been invested. I just mentioned three, but there's a lot of money invested in this. Microsoft also invested a lot of money on this, and it has been in the news for a long time. And if you compare the traditional machine learning algorithms with the deep learning algorithms with respect to the size of the data, as you can see in the figure, traditional machine learning algorithms performance has been saturated after some point of time. You observe that, right? And as the size of the data increases, deep learning algorithms are doing exceptionally well as compared to the traditional machine learning algorithms. And at the edge of internet, we have lots of data, isn't it? Tons of data has been produced every day, isn't it? So we have lots of data, and with lots of data, deep learning algorithms are doing better as compared to the traditional machine learning algorithms. Okay, that is also one of the reasons why we are moving towards the deep learning framework. Am I fast, or is this phase okay?
Is it okay, sir?
Okay, all right. So these are the different paradigms in the deep learning framework. Probably, I mean, correct me if I'm wrong, sir, organizers. I think these are the different things that this FDP covers. Based on the top titles, I've got this information. Supervised learning, unsupervised learning, reinforcement learning. These are the different paradigms in the supervised learning: feed-forward neural networks, convolutional neural networks, sequence modeling like RNNs and its extensions, encoder-decoder architecture, and in unsupervised learning, autoencoder, generative adversarial networks, and in reinforcement learning, deep reinforcement learning also will there. Okay, so if you see the feed-forward neural network, this is the main agenda of this particular talk. Okay, this session in neural network basics itself will introduce this feed-forward neural network, but other things will be introduced solely in the next sections. So at the high level, if you look at all these diagrams, neural networks are either encoders or decoders or combinations of both. What do you mean by encoder? What do you mean by decoder? And why is it important here? Say for example, I ask you to slap someone. Okay, so this information of, I mean, this input of, I'm saying that slap someone, you're hearing it through your ears, and this is reaching through your mind, and somewhere you're encoding this information and representing it, and that representation you're using your experience, you're decoding it, and finally you're taking action of raising your hand, or you may be saying that no, I don't want to slap you, isn't it? So all this process is happening, right? So you have a connection somewhere between your ear and mind. So some part of the brain is responsible for this hearing, isn't it? So it gets some information, it input from the ear, and it encodes that information, it stores in some representation and with the experience, and that information it decodes that and it takes the action. Okay, so all this process is happening in our mind, right? Similarly here also, when you give some input, you encode that, and you come to a compact representation which is much smaller than the actual input. So based on this representation, either you predict, say for example, when you see something like to determine whether it is an animal or a bird, what is the compact representation that you get from the figure, whether it has a four legs or not. That is the simple representation that is sufficient to judge whether it is animal or a bird, isn't it? So this you can get through this encoder, that representation. Using this representation you can predict. Yes or no? So similarly, if you want to get some machine translation, say for example Hindi to English. So given a Hindi text, you should be able to convert into English text, isn't it? So what you are doing is that you are getting this Hindi into some compact representation, and you are seeing what are the words for this, and then you are decoding it into English, isn't it? So all these things are happening in your mind, isn't it? So similarly, this artificial intelligence or deep neural networks also mimics this brain, isn't it? So it has two parts: encoder, which find the patterns in a raw data to form compact and useful representations, and decoders, they generate high resolution data from those representations that are learned by the encoder. Okay, and this generated data, I mean the data generated by the decoder is either new example or a descriptive knowledge, isn't it? So encoder or decoder can be completely different. For example, you say that you want to do a task of captioning an image. In this case, what is the encoder? Encoder is the image encoder, whereas the decoder is the text decoder. Okay, so you can have any encoder, you can have any decoder. All right. So in feed-forward neural network, we'll discuss one by one now. So in feed-forward neural network, data passes from input to the output in a single pass without any state memory of what came before. It don't have any state memory. It doesn't remember anything. It just passes the information to layer to layer and finally to the output layer. Okay. So most of the networks that we have in deep learning are feed-forward neural networks. But when somebody says feed-forward neural network, it usually means that multi-layer perceptron. Okay, I mean densely connected multi-layer perceptron, fully connected neural network in simple words. And somebody says that it is feed-forward neural network, it is fully connected. What they mean is that feed-forward neural network, usually. Okay, but see, convolution neural network is also a kind of feed-forward neural network. Okay, so there are multiple feed-forward neural networks, but in this particular case, what I mean by feed-forward neural network is densely connected multi-layer perceptron or a fully connected neural network. Okay, so in this
So
encoder is a dense
can
encoder,
you give
and
example for it?
convolution neural network, here it is a convolutional encoder. Here it uses the spatial invariance trick to efficiently learn local patterns. Okay, what do
Can
you
you
mean
give
by
example,
spatial
sir?
invariance trick? Special invariance trick means, for example, means that, say for example, you have an image. In that image, bird beak or a cat ear at the top left of the image has the same feature as a bird beak at the bottom right of an image, wherever the object is present. Say for example, wings or a bird beak or legs. Irrespective of wherever it is present in the image, it learns the same feature for the legs. It learns the same feature for the beak, or it learns the same feature for the wings, irrespective of wherever it is present in the image. Okay, but that is not the case with feed-forward neural networks. That is the disadvantage with this feed-forward neural networks. Okay, in RNN, in case of RNN networks, we have cycles and therefore a state memory also there. So it remembers things based on the previous state, it predicts the next state, and it can be unrolled in time to become a feed-forward neural network. You can unroll this neural network and it can become feed-forward neural networks. And this RNN also shares parameters, but it across the time, but not across the space. Whereas if you take CNN, they share parameters across the space, not across the time. But recurrent neural networks, they share parameters across the time. Okay. Acha, this is a brief introduction. You don't think that, with to everything, details will be discussed in the next sections. All right, so I just wanted to give overview of the FDP also. That is why I kept this slide. Okay, so in case of encoder decoder architectures, if you observe here, last three networks we are making prediction. We are not making any prediction here. If you see the fourth architecture, there is no prediction. Whereas if you see here, we're making some prediction. Okay, so instead of making prediction here, encoder decoder architecture generates a high dimensional output using the decoder by unsampling the compressed representation given by the encoder. Okay, so this is mostly used for image captioning or machine translation. What happens in image captioning? You give some image, that is, using this encoder, you can learn some compact representation. Using that representation, you can decode and say that, okay, this is the image of a dog. This is the image of a man holding dog. This is an image man riding horse. So things like that you can give, right, by decoding whatever the representation that you got from the encoder. Okay, so it is used for those kind of tasks. You will not predict, but you will generate some high dimensional data based on the input in some other format. All right. So autoencoders, the fifth one I'm talking about, autoencoder is one of the simple forms of unsupervised learning to generate an exact copy of the input data. Why do we require the exact copy of the input data? I'm so much surprised. This must be running in your mind, isn't it? So the thing here is that in a process of generating the exact copy of the input data, in between you have representation, isn't it? You're using encoder to generate the representation for this image, and this representation is much smaller than the input image. Okay, so in that process, what is happening is the network is forced to learn the most meaningful representation from the data. Okay, and this representation can be used for other kind of tasks because it is much smaller than the input data. Okay, so this is a fundamental idea of representation learning. It is central to the generative models, that is this generative adversarial network. Okay. In generative adversarial network, we generate new realistic samples from a particular representation. From a particular representation, we generate samples like fake images or fake, images that are very close to the original images, or the faces that are very close to the actual faces, or the poetry that is very close to the actual poetry, or a painting that is very close to the Picasso paintings. So all these different fake things that we can generate using this generative adversarial networks, popularly known as JAN. Okay, so in its simplest form, the training process has two networks. One network is called the generator. You can see that, right? Generator. The other network is the discriminator. So the task of generator is to generate the fake images and trying to fool the discriminator. And the task of the discriminator is to predict whether it is real or fake given some new image, isn't it? So that is the brief introduction about that. And in case of reinforcement learning, you might be aware of what is reinforcement learning, right? Reinforcement learning is a framework for teaching an agent how to act in the world in a way that maximizes the reward. So he takes some action, he gets the reward. Reward can be actually a punishment, or it can be some value. Okay, some gift kind of thing. Okay, so he has to act in a world in such a way that his reward is maximized. Okay, not the punishment. All right. So when the learning is done by a neural network, we refer to this as a deep reinforcement learning. There are multiple ways of doing this deep reinforcement learning. Means that agent takes action, he gets the reward. Agent takes the action, he gets the reward. So this agent has to act in such a way that this reward is maximized. That is reinforcement learning. If this task of learning through action and reward, if you do it through neural networks, then you call it as deep reinforcement learning. Okay, so this is a brief introduction to the different paradigms in the deep learning. There are few networks that may not fit into these 7 architectures also. Exploring all of them is beyond this, beyond the scope of this. All right. So if you observe so far, what is deep learning? Deep learning, precisely, deep learning is a branch of machine learning wherein neural networks learn from large amounts of data. Simply. That's all right. So we have gone through so many things. We have seen what is machine learning, what is deep learning, how deep learning extracts its patterns, different architectures of deep learning, different applications of deep learning. All these things we have seen, right? So, but then the summary of all that is that deep learning is a branch of machine learning where neural networks learn from large amount of data. Right. So this is, we can take it from the previous slides, isn't it? So then we've been talking about this neural network. We're saying neural network is that, neural network is this, all these things we're talking about that, right? What is neural network? What is neural network? Let's see that. So we'll see the artificial neural network basics. So human brain has around 80 million to 100 billion of neurons, isn't it? Before that, let me tell you something. What I mean, if you see the brain as a black box, okay, what it does, it takes inputs and gives outputs. Similarly, artificial neural networks also, if you see it as a black box, it takes inputs and gives outputs. Okay, so which was actually designed, artificial neural networks are actually designed to mimic the functionality of the mind. Okay, so neurons in the brain. Okay, so human brain has actually around 80 billions to 100 billions of neurons performing various functionalities depending on where they are located in the brain. Okay, so depending on where they are located in the brain, they perform different functionalities. For example, some part of the brain controls the vision, and some part of the brain is involved in interpreting of pain and touch, and some part of the brain controls the speech, some part may be controlling the smell recognition, and some part may be controlling the touch. All these things are there, and so forth. Correct. But irrespective of the location in which where they are, these neurons have some common structure. All right. So these neurons have some common structure. We'll see what is the structure. Most importantly, they have 4 parts: dendroids, soma, axon, and synapse. Okay, I think I have next another slide for that. So let's see in brief what is artificial neural network. Artificial neural network is an interconnected group of nodes inspired by a simplification of neurons in the brain. Okay, you can see that, right? Brain, if you zoom in, you have so many neurons connected to each other, connected to each other through some interconnected network. Okay, so one neuron is connected to another neuron through this synapses and dendroids. Okay, so the original goal of this artificial neural networks is to mimic the human brain with the complete functionality, but the current attention is limited to performing specific tasks. Specific tasks like classification or regression or fraud detection, something like that. And it is used in variety of tasks computer vision, speech recognition, machine translation, social networking filtering, playing board, video games, and so forth. Alright, so if you see this biological neuron, you see there are four important things: dendroid, cell body, that we also call as soma, axon, also synapses. These terminal points are the synapses. Okay, so what is dendroid in the biological neuron is that it receives sparking signals from the other neurons. It receives spiking signals from the other neuron. So these are the inputs to the neuron. Okay, dendroids are the inputs to the neuron. So it receives spiking signals from other neurons. And the width of the dendroid determines the weight associated with it. If the width is big, then more weight. If width is very thin, then it is very low weight. Then the cell body, or soma we call it, it receives these spiking signals from the dendroids, that are the inputs, and integrates them. If the resulting signal voltage, after integration you get the resulting signal, right? If the voltage of that signal is greater than some threshold, then that neuron fires and sends the signal to the axon. If it is less than threshold, then it won't send any signal. All right, so what is happening is that in dendroids, it's receiving the input through dendroids and integrating. Somehow it is integrating these signals, and resulting signals voltage, if it is greater than certain threshold, then it is firing that neuron and sending signal through axon to the next neurons, connected neurons. Correct. So that is where axon plays a role, that it propagates the sparking signals generated by soma to other neurons and connects to other neurons through synapses. So whatever the signal that is generated by this soma, this synapses carries that and it sends this signal to other neurons through synapses. Okay, so synapses act as a memory organ in the brain. It connects axon of last neuron to the dendroid of the next neuron. So the synapses is a connection point where it connects the axon of this neuron with the dendroid of the next neuron. So this is the biological neuron structure. So researchers have designed similar thing in artificial neural networks also. They come up with the artificial neuron. In this case also we have inputs, dendroid-like structures. What happened to my mouse? Okay, yeah. So dendroid structures, those are called inputs. And here we have weights. And this is the linear combination where we take the integration of all these inputs and the weights. And then after we get this net weight here, we give it to the hard limiter, which decides to some function. If the resultant is greater than certain threshold, then you forward that, otherwise you won't. All right. So this is the activation function, this function that we are talking about. After taking sum from each and individual outputs, if this x is greater than certain threshold, then y would be +1, otherwise it is -1, the output. Okay, that is how we decide. We'll revisit this again. So neural network is a combination of multiple such neurons, correct? So from layer to layer, this is how they are connected, isn't it? So this is a simple example of neural network. A single neuron, we call it as perceptron. Single artificial neuron is equivalent to perceptron. This is also equivalent to logistic regression, which we will see in detail. So, all right, everything is fine. So we are trying to mimic the human brain. That is why we have created neurons, artificial neurons like biological, which has a similar functionality of biological neuron. We have similar things there and here. Everything is fine. We have formed a network of artificial neurons. In contrast to the biological neural network, we have now artificial neural network. Everything is fine. What are we doing this for? And what are they used for? It is used for many problems. I have listed out very few here to maintain the continuity to the next slide. So it can be used for regression, classification, noise reduction, and prediction. Okay, and many other things. Okay, let's look at this regression and classification problems to understand the machine learning basics. So my main intuition behind keeping this regression and classification problems and a simple regression, simple classification problem is to understand some machine learning basics which are essential to understand the further sessions. So, what is supervised learning, and what is the problem in case of supervised learning? What is given as an input to us, what it is expecting as an output in case of supervised learning. In case of supervised learning, we are given a training set of pairs, M examples or M instances, isn't it? Or the training data of M instances, correct? In which each instance or example is a pair. Okay, what is that pair? Xi, yi. What is xi in this? Xi is the feature vector of t dimension. And what is y? What is yi is corresponding target variable. Okay, say for example, if you take a regression problem, xi could be size in square feet and yi could be price of the house. If you want to determine the price of the house given a new instance, correct? So, and yi is a target variable. Target variable could be either continuous or discrete. If it is continuous, then we call it as a regression problem. If it is discrete, we call it as a classification problem in supervised learning. Okay, so given this input data of pairs xi, yi with m examples, xi, yi for I equal to 1 to m, what is our task? Our task is to predict for a new instance, right? Given a new instance for which we only know the feature vector but not the target variable. So given a new instance, we should be able to predict the corresponding target variable. So this is the problem statement briefly. For example, suppose I want to predict the housing prices. Okay, housing prices. What is the price of a house? What is that I have given is that we collect the data regarding house prices and how they relate to size in feet, as you can see in the figure. So size of the feet is the input vector and price of the house is a target variable. So if we collect data something like that, I just took one variable here, that is size in feet, but you can take multiple variables like size in feet, number of bedrooms, number of floors, age of the house. Like that, you can take multiple dimensions. Just for the simplicity of understanding, I just took one variable here, that is size in feet, and I just wanted to understand how is it related to price in dollars. Correct. So given this input, what machine learning algorithms does? Is the question. Okay, you know machine learning, right? So it chooses each of this, like the decision function, like you chooses the model, like whether it is a linear regression, logistic regression, or neural network, some decision function. It also has to choose the loss function, either it could be a mean square loss, loss entropy loss, 0-1 loss, or hinge loss. There are various loss functions. And your target is to minimize that loss using the optimization process. Say for example, gradient descent, using the gradient descent. Okay, so this is machine learning flavor. Correct. So let us, your decision function says that you have to express the outcome or the prediction y dash in terms of some function of x. Okay, some function of x. That function you have to decide what is that. Okay, and loss function, which gives some scalar value, you have to minimize that loss function, which basically minimizes the difference between the predicted and actual values. This y cap is the predicted, yi is the actual, and you want to minimize the difference between these two. Okay, so loss is expressed in terms of the difference between actual and the predicted values. So let's see linear regression, which is a solution for the regression problem. You understood regression problem, right? You have given set of xi and yi pairs, m instances of that, in which yi is a continuous value, like this. Price is a continuous value, right? It's not a discrete value. So given that, given a new house, you should be able to predict the price of that house. This is a simple regression problem. Okay. So what the machine learning algorithm, generally what machine learning algorithm does is, given a training set, it passes that training set to the learning algorithm. Learning algorithm outputs a function or a hypothesis or a model. These are the different terms that we use for the same. Okay, so it outputs either hypothesis or a function or a model. Okay, once you get that model, you pass a new instance to this model and estimate the price or predict the target variable. Okay, so this is the general procedure that happens in machine learning algorithm. Once you have the training set, you pass it to the learning algorithm. Learning algorithm outputs the hypothesis. Once you get the hypothesis, you pass a new instance to this hypothesis and it would estimate the prediction. Correct. This is the general procedure. Now the question is, what is this hypothesis for a linear regression? Okay, so this hypothesis in case of linear regression is expressed in terms of a line. Is a line which passes through the data. So what is the equation of the line? Line, in case if you have a single variable, it is a hyperplane if you have multiple variables. Don't just fix it to line, but if you have multiple dimensions, it is a hyperplane. You call it as hyperplane. That also we'll see. I have next slide. I have slides for that. So hypothesis in case of linear regression is expressed as a line. For a single, I'm talking about a single variable. That is why I'm terming it as line. Okay, following me or following me? Is that fine or am I too fast?
Yes, sir. It's okay,
Can
sir.
somebody respond?
Yes, yes. Okay, sir.
I cannot see the chart box actually. Maybe you have.
Okay, okay. Yeah, it is fine.
Oh, I couldn't hear you guys. Okay.
Yes, yes. It is
Okay,
fine.
okay. Thanks. There is some problem with this earphone. I could not hear what.
No, no, no. We are hearing.
Okay.
Correct.
All right. Now the question is, okay, where am I? So hypothesis in case of linear regression is represented as a line in case of single variable. In case of multiple variables, we represented it as a hyperplane. So if you see, what makes the line different? Two parameters, right? Theta naught and theta 1. It is in the form of ax plus b if you observe, and which is the equation of the line. Ax plus b is the equation of the line, right? A equal to theta 1 here and b equal to theta naught in this case. So here y is a linear function of x, some linear combination of input variables. That's all, right? And theta are the parameters here. Okay. And linear regression with one variable we call as a univariate linear regression. Linear regression with multiple variables, we call it as a multivariate linear regression. So first let us look at univariate linear regression, then we'll go for multivariate linear regression. And just remember, these are all to understand the basics of machine learning. Okay, now the question is, you're saying that my model is line, but which line? There are many lines possible. Many lines may go through the data, many lines may passes through the data, isn't it? So there are many lines possible. How can you select the best line? Which line is the best? Okay, that is where the cost function helps us. A cost function lets us figure out how to fit the best straight line to our data. What makes the line different? Two parameters, theta naught and theta 1. If theta naught, theta 1 different, then line will be different. Okay, so which is the best line? The line that minimizes the difference between the actual and the estimated prices. Correct. One line may be predicting it as a different value. Correct. Each line predicts the output as a different value. Correct. So the line that minimizes the difference between the actual and the estimated prices is the best line. Can I say that? I can definitely say that, isn't it? So the line that minimizes the difference between the actual and estimated prices is the best line. So what is our objective? I have to learn this line in such a way that minimizes the difference between my hypothesis, that is the prediction value h of x, and y, which is the actual value, for each and every example in the training set. Correct. So that is my objective. My objective now is very clear. So I have to choose two parameters, theta naught and theta 1, in such a way that h theta of x is close to y. That is my objective. Correct. How do I do that? So my objective is clear now. I just want to minimize the difference between h theta of x, which is the prediction, and yi, which is the actual value. So I just took squared loss here. There is a reason for this. I am not going to the details of that, but I just took the squared loss. Anyone is speaking? Anyone has some doubt? I'm hearing some noise actually.
No, no.
Okay. Okay, so I just wanted to minimize the difference between the predicted and the actual values. This is my objective. I just want to minimize that loss function. How do I achieve this? How do I minimize the difference between that? How do I learn this theta naught and theta 1 in such a way that this value is minimized? Is the question. That is where gradient descent helps us. What is gradient descent? Again, some new term. We've been introducing so many new terms. What is gradient descent again? This is very new, abruptly something coming here. What is gradient descent? What is gradient first of all? If you take a line, say for example, some simple function, I just took line y equal to mx plus b. Okay, so what here, what is gradient in this or a slope in this? M represents the slope or the gradient, isn't it? And y is how far we are up, and x is how far we are along, and b is value of y when x equal to 0. Okay, so if I say that this line is of positive slope, okay, you can see that, right? The in the that plus wala symbol, plus symbol wala cycle with plus symbol wala. You can see that, right? You can say that is positive slope, correct? Similarly, this negative wala is a negative slope, isn't it? So you, by seeing itself, you're saying that it is a positive slope, it is a negative slope, and there is no slope in the middle figure. That's what we can easily say that from that, right? What do you mean by that? What do you mean by positive slope, negative slope, or no slope? Okay, so if this gradient is positive, then it is a positive slope. If this gradient is negative, then it is a negative slope. If it is 0, then no slope. Correct, isn't it? So that is how you can calculate, right? So if you want to determine slope of a function with respect to a particular variable, how is the slope as you vary that variable? Say for example, in this case, what is the slope as you vary x? That is what it is determining, right? M is that, right? M is what is the slope as you vary x? If you want to get M, is it fine to take derivative of this function with respect to x? Suppose if I take derivative of this function mx plus b with respect to x, what would I get? Partial derivative of this function with respect to x. I would get M, right? Which is the slope of that function as you vary x, isn't it? So now from this, I can summarize that if you want to get a slope of or a gradient of a function with respect to a particular variable, you take derivative of that function with respect to that variable. So can I say the gradient is just a vector of partial derivatives? If you want to the gradient with respect to multiple variables, you can take the derivative with respect to each and every variable, and derivative of all these variables, derivative with respect to all these variables together can form a vector. And gradient is a vector of all such partial derivatives. So that is gradient. And what is gradient descent? Okay, but before that, see that, let us graphically represent the convex cost function. The cost function that we have, that we want to minimize, it is convex. Okay, now, that is the square loss with the hypothesis of theta naught plus theta 1 x, which is a convex function. So for simplicity, in the first figure, I just took one variable theta 1, how it varies with respect to theta 1, j of theta. This is the function that you want to minimize. All right. Krishna sir, I just one request to you.
Yes,
If you want to say something, sometimes I couldn't hear with this earphone. Just message me if you want to say something to me. Okay.
No, definitely we are hearing you.
Yeah, I mean, in case if you want to say something.
Yeah, sure. Yeah. I will inform.
Thanks. So now, so the cost function that we want to minimize is like a convex, isn't it? And what is our goal? To reach to this value point, isn't it? We want to minimize this j of theta, and we want to find theta 1 in such a way that j of theta is minimized, correct? So I want to reach to this point. It means that I want to find theta 1, this theta 1, where it is minimum, correct? So I want to reach to this point. So, but when I randomly initialize these theta values, similarly, in case of if you take multiple variables, theta naught and theta 1, in 3D dimension, it may look like this, like a bowl, and you want to reach to the middle of the bowl. That is where bottom of the bowl. correct? So that is your objective, correct? So when I randomly initialize these values, theta naught or theta 1, when I randomly initialize, it may not be the point that is where it is minimized, correct? I have to gradually reach to this point. How do I reach to that point, that minimal point, gradually? Is the question. Say for example, when I initialize this theta naught, theta 1, it is here. What is the slope of this function here? Which is negative, correct? The slope of the function here is negative. Okay, so and I have to move forward to reach to the minimal value, correct? It means that I have to increment theta 1 value. I have to increment this theta 1 value when it is negative slope, correct? So when the slope is negative, I have to increment this theta 1 value. Similarly, if the slope is positive, in the second diagram you see, if the slope is positive, what I have to do? I have to decrement this theta 1 value to reach to this minimal point, isn't it? Now it is clear, if the slope is negative, we have to increment theta 1 to reach to the minimal value of j of theta. If the slope is positive, we have to decrement theta 1 to reach to the minimal value of j of theta. Very simple, correct? Very easy to follow. I just have to do addition if the slope is negative. I just have to do subtraction if the slope is positive. That is all I have to do, isn't it? To reach to the minimal value. So is this okay? I initialize theta naught and theta 1 and I repeat this procedure. And how do you get this slope, by the way? You can get this slope by using a slope or this gradient by using partial derivative of j with respect to that variable, correct? So I just have to repeat theta j equal to theta j minus alpha times derivative of j with respect to theta j. So what you are doing, if this quantity derivative of j with respect to theta j, which is actually slope, if it is negative, what you are doing, negative times negative, which is positive, you are incrementing theta j. Similarly, if it is positive, negative times positive, which is actually negative, it means that you are decrementing theta j, correct? That's all you are doing. When it is positive, you are decrementing. When it is negative, you are just incrementing it. Okay, what is this alpha? Step size. How much step size you are taking when you are incrementing or decrementing? Okay, that's all. Okay, and derivative of j with respect to theta naught is this, and derivative of j with respect to theta 1 is this. Okay, you can just calculate, you will get this, you will arrive at this, correct? All right, any doubts I can take? Yeah, otherwise I'll proceed. So this we call as a gradient descent algorithm. This whole process of initialization and repeating until convergence, theta j equal to theta j minus alpha times derivative of j with respect to theta j, the whole thing we are calling it as a gradient descent algorithm. All right, you have other things also with simple variation.
So this gradient descent algorithm is applied only for this convergence.
Yeah,
is
to
this,
optimize for the optimization.
yeah, okay. Optimization of synaptic signals.
I have not yet reached there. I am just trying to optimize some simple objective function. Yeah,
Okay.
in any case, yeah, you have some objective in any case, any of the models that you want to optimize.
Okay.
For that optimization procedure, you are using gradient descent. There are other optimization techniques also, like batch gradient descent.
So we have to memorize all this algorithm. We should be thorough with that.
Yes.
Okay.
There are various optimization techniques. You have to select one based on the problems. This is univariate linear regression. So far, whatever that we have discussed, that is with a single variable, size in square feet, right? Now let's go to the multivariate linear regression. Linear regression with multiple input variables or features. So the same example I took again. Size of the square feet is one of the feature. Number of bedrooms is another feature. Number of floors, age of the home. All these are the different features. So if you see this, it is a 4-dimensional vector. Input feature is. It's not a single dimension now. Okay. So now we have multiple dimensions. That is why it is multivariate linear regression. Okay. So previously our hypothesis is a line theta naught plus theta 1 x. Okay. With multiple features, now our hypothesis is hyperplane, that is theta naught plus theta 1 x1, theta 2 x2 plus theta 3 x3 plus theta 4 x4. Correct. So Um, so if I take x naught as 1, I can write this as this, right? I can just write this h theta of x as this, isn't it? If I assume x naught equal to 1, theta naught x naught plus theta 1 x1, so on. So this is just dot product of these two vectors, isn't it? Theta naught x, sorry, theta and x. If I say theta is one vector, x is another vector with four elements in it: theta naught, theta 1, theta 2, theta 4, and similarly x has four elements in it: x naught, x1, x2, x3, x4. Sorry, 5 I think. Yeah, 5. So then it is theta transpose x. I can just write that, right? Isn't it? So you can represent in the vectorized notation as theta transpose x. Okay. So gradient descent for multiple variables also same. That is, you have to instead of two parameters in earlier case, you have n plus 1 parameters now, where n is the number of features. Theta naught to theta n you have now. So you have to update each and every theta value now. You have to learn all the parameters, theta naught to theta n. Procedure is then theta j equal to theta j minus alpha times derivative of j with respect to theta j. So one thing that you have to remember here is that you have to simultaneously update for every j equal to 0 to n. What do you mean by simultaneously updation is, see, when you are updating theta naught, theta 1, theta 2. Okay, so this derivative part may have, say for example, you are updating theta naught, theta 1. Okay, this derivative part has theta naught also. Okay, so when you are taking theta naught value, you have to take theta naught from the previous iteration, but not the updated theta naught. Okay, so it is the case with every parameter. So when you are taking this, when you are computing this gradient part, you have to take the values from the previous iteration, but not from the current iteration. All right, so that is what I mean by simultaneously updating different theta j values. Krishna Garu, I mean,
Yes, I'm requesting Anubhuti Sharma, please stop sharing. You have shared Anubhuti Sharma. Anubhuti Sharma. Yes, sir, you can present now again, please.
Dr. Krishna,
Yes,
this
yes.
actually takes time. So
Okay.
whenever you want to give break, just let me know. I'll stop there.
Yes, yes. Yes, yes. You can present now, sir.
Yeah, I mean, just let me know whenever you want to give break. That's fine.
Yeah, yeah. 5 to 10 minutes, then we
Hmm.
can.
Can I present now, or is that
Yes,
visible?
yes.
Okay.
Yes, you present.
Is it not visible, or should I again present?
Again present, it is not visible.
Okay.
So is it visible, sir?
Yeah, yeah, visible. Yes, sir, continue.
Okay. Okay, so now comes to the regularization, which is another key concept that you have to learn from the basic machine learning basics, which is also helpful in case of neural networks. Okay, regularization. Before I talk about regularization, and we'll see why we require this regularization. Let's say simple data. This is the data I have generated using that green curve, that is sine 2 pi x curve. Okay, so this is the data of 10 points, blue points, that I have generated from sine 2 pi x and added some noise, little bit noise there. Okay, so 10 points I have generated and added some noise, bit of noise. Okay, so but the basic function from which I have generated is sine 2 pi x, that is the green one. And suppose if I fit a 0th order polynomial function to this, it means that my hypothesis is just theta naught, nothing else. My hypothesis is just theta naught, nothing else. That means 0th order polynomial. Okay, no input data. Then my model looks something like this, right? Horizontal line. You can see that it is not a good fit to the actual data, isn't it? It is underfitting. Similarly, if you fit first order polynomial means your linear regression function, that is theta naught plus theta 1 x. Okay, polynomial is first order. Okay, theta 1 x, just x, not x square, first order. So then in this case it is just a line, and this is a better than zeroth order polynomial, but it is also not good fit. Suppose my function is of third order polynomial, that is theta naught plus x, theta naught plus theta 1 x plus theta 2 x square plus theta 3 x cube. Remember, I'm just talking about one input variable. Okay, theta naught plus theta 1 x1 theta 2 x square theta 3 x cube. That is my model. So it is very close to the original function, isn't it? So this red wala is my prediction or the model, and the green wala is the actual underlying function from where I generated this data. So it is reasonably good function, isn't it, for that input data. Suppose let's increase the polynomial order. Suppose I have taken 9th order polynomial. You see this very beautifully fitting to the data, isn't it? It is going through each and every data point, no error at all, zero training error. Correct? Zero training error, which is going through each and every point, means that it has got zero training error. Okay, which is absolutely fine as if we consider this loss function h theta of x minus yi, because it is zero if you consider 9th order polynomial. But do you think that it is a good representation to the input data? Because we know the underlying function from where we generated. Do you think if I give a new instance, which is again generated from the underlying function, will it be predicted correctly using this function? It's not, right? Because it is oscillating too much. Give me 1 second. Sorry for the disturbance. Sorry. Okay, I'll continue. So if you see this one, which is actually fitting very well to the training data, but it is not a good representation. It means that test error would be very high if you follow this model, because it is oscillating too much in between the data points, input data points. So this model has got lot of variance. Okay, am I audible?
Yes, sir.
Yeah, you are audible. You are audible.
Yes.
Audible.
Yeah. So it has got lot of variance. So if you observe, why is this happening? Why is that lot of variance? Why is that lot of oscillation in between the data points? If you observe that the corresponding parameters theta naught to theta 9, okay, which is termed as w naught here. So w is same as theta. Okay. So for m equal to 0, the range of the values is low. M equal to 1, range of the values is low. M equal to 3 also reasonably low. But if you see, when m equal to 9, that is 9th order polynomial, if you see the range of these values, it is too high, isn't it? It is too high. So that is the reason why this curve is oscillating too much between these data points, and it has got lot of variance. Correct. So how can you control this? How can you control these parameters from growing? Okay, so the idea is to penalize high weights that contributes to high variance and sensitivity to outliers, isn't it? So we just have to penalize these weights, isn't it? How do we do that? We can just add these theta values to the cost function, where we are trying to minimize the cost function with some weightage lambda, isn't it? So this theta L is a regularization term that you are adding. Theta L means L normalization. Okay. If it is L equal to 1, then it is theta 1 plus theta 2 plus theta 3, so on. Absolute value of each of them. Absolute value of theta 1 plus absolute value of theta 2, and so on. If L equal to 2, then it is square root of theta 1 square plus theta 2 square plus so on. If it is 3, then is cube root of theta 1 cube plus theta 2 cube plus so on. Okay. So what you are essentially trying to do is that you are trying to penalize these theta values, and that will stop them from growing too big. That is the idea of regularization here. So which will avoid overfitting problem. What is overfitting? Overfitting is performing too good on the training data, but too worst on the testing data. So that scenario we call as overfitting. So to avoid the scenario of overfitting, we add the regularization term. There are other ways of controlling this also. You can have more data. That is also one of the ways. You can other regularization techniques. There are many things which will be discussed in the next coming sections. Yeah. Anyone has doubt?
No.
Okay. Yeah. So that is about the regression. Okay. Now coming to the classification. Logistic regression for the classification. So this is like linear regression model is for the regression problem. Logistic regression model is for the classification problem. So this is also one of the basic concepts to start before we start the neural networks theory. Okay. So unlike in case of linear regression, the output here is a probability, that is h theta of x, the prediction gives the probability that y equal to 1. Okay, so this is for a binary classification, y equal to 1 or y equal to 0. Okay, so the output gives the probability that y equal to 1 given x and theta. Okay, so this is the model. H theta of x, this is my model. Hypothesis is equivalent to z of theta transpose x. Theta transpose x is the previous model, isn't it? Theta transpose x is the previous model, the model that we have used for the linear regression. So I'm just passing this to some function. That function name is sigmoid function. Okay, so this is sigmoid curve. I'm just passing this theta transpose x. This is the linear model that I have got in the previous model, is that linear model. I'm just passing it to the sigmoid, which converts this model to the probability. Okay, that is 1 by 1 plus e power minus z. Z of z equal to 1 by 1 plus e power minus z. It means that g of theta transpose x is equivalent to 1 by 1 plus e power minus theta transpose x. Okay. So to have this to be positive, for positive instances, theta transpose x should be large positive value, and for the negative values, that is, this is the, I have two classes now, y equal to 1, y equal to minus 1. Okay, so for the positive values, theta transpose x should be large positive values. What happens if theta transpose x is large positive value? It is in the denominator. It is 2.31, right? Exp, I mean, es value is 2.31, something like that, right? So 2 power 31 power minus of large positive quantity, which is nearly equivalent to 0. So it means that it is predicting this as correctly. Okay. Similarly, if theta transpose x is a negative value, then negative times negative is a positive. Large positive value here means the whole thing is almost close to 0. It means it is classifying it as 0. Correct. So this h theta of x, if it is greater than 0.1, you can predict it as 1. You can predict it as minus 1 or 0 if h theta of x is less than 0.1. Sorry, it is not 1. It is 0 or minus 1, depending on how you notate it. All right. So the problem here is, in case of logistic regression, is given these pairs x1 y1, x2 y2, so on xm ym, where xi is the feature vector and yi belongs to either 0 or 1. Okay, which means binary classification. Your model is h theta of x equal to z of theta transpose x, where z is a sigmoid function which is equivalent to 1 by 1 plus e power minus j. Okay, and similar thing, isn't it? Only thing is that your function has changed. H theta of x has changed. Earlier it was just theta transpose x. Now it is z of theta transpose x. Everything else is same. Earlier yi is a continuous value, now it is a binary value, 0 and 1. Okay, but the parameters that you have to learn are the same. Theta naught, theta 1, so on, theta d. Isn't it? So model is different, output variable is different, but the parameters that you have to learn are the similar, theta naught to theta d or theta n. Correct. So now coming to that earlier case, we have used square loss, isn't it? Our objective is to minimize the difference between the predicted and the actual values. But here, the outcome of the hypothesis is not a prediction, correct? It is the probability that y equal to 1. It's not a prediction. Okay. Even if you convert that into a prediction and use squared loss, it will result in a non-convex optimization. It means that the curve, that whatever that you have seen, like a bowl structure wala, it's not a bowl no more. It means it's a zigzag wall. Okay, non-convex. Okay, so with that you may stuck in a local optima. So for that reason, we have a different objective here. The objective function in logistic regression is this. Sum over I equal to 1 to m, which is the number of instances. yi log h theta of xi. H theta of xi is the prediction. Yi is the actual one. And 1 minus yi log 1 minus h theta of xi. This is the objective function that I want to minimize in case of logistic regression. Let us see the intuition behind this logistic regression. So this is the intuition. What is happening here? If I separate this, if I see this, I have two class labels, 0 and 1. If yi is 0, then what happens? I am considering only this part, isn't it? Only this part. If yi equal to 1, it means that my output class label is 1. It means that I am just considering this part, isn't it? So I think minus should be there. I've just missed it. Anyway, so if yi equal to 0, I'm just considering this part. Sorry, this part. If yi equal to 1, I'm just considering this part. So I can write it as this, right? Yi equal to 1, then minus log h theta of xi. If y equal to 0, minus log 1 minus h theta of x. I can write that equation as this, right? So what is happening? What is our motive behind the cost function finally? If the prediction is correct, then we shouldn't finalize the cost function. Means that we should add 0 cost to it. Correct. If the prediction is wrong, I should penalize it with some high number. Isn't it? So if the prediction is wrong, I should add some positive number to this cost function. If the prediction is correct, I shouldn't add any positive number. I just have to add 0 to it. That is what the intuition behind any cost function, correct? When it is correctly predicting, you say it is 0 cost. When it is wrongly predicting, you say some positive cost. Okay, and you want to minimize the cost, isn't it? So whether this function is satisfying that criteria or not, let us look at this. This is the log plot. Okay, so if y equal to 1, h theta of x equal to 0. Let us look at a scenario where y equal to 1, h theta of x equal to 0. It means that prediction is wrong, isn't it? When h theta of x is wrong, what is log x theta of x? Which is minus some value. Okay, minus of minus is a positive value, isn't it? It means that you are adding some positive value to this cost function. Similarly, when y equal to 1, h theta of x equal to 1, means that correct prediction, you should add 0 cost to it. What is log 1 here? Log 1 is 0, isn't it? Log 1 is 0 here, isn't it? So you are not adding any cost to the cost function. Similarly, if y equal to 0, h theta of x equal to 1, then you are adding some cost to it. If both are same, you are not adding any cost to it. So that is the intuition behind it. So you can see this. If y equal to 1, then h theta of x, as h theta of x close to 1, cost is decreasing. When y equal to 0, as h theta of x close to 0, cost is decreasing. You can see that, right? So this is the intuition behind the cost function that we have adopted. The regularization in this case also same. You can just add some extra term here, that is L normalization of the parameters. Gradient descent concept also same. you have to update the parameters theta j equal to theta j minus alpha times derivative of j with respect to theta j. Only thing is that j is changed here. What is changed in j? The prediction h theta of x is changed little bit. All right, I think we have finished the machine learning basics. Now let's go to this neural networks basics.
So can we, sorry to interrupt you, can we take a break here?
Yeah, we can take break. Absolutely fine. Very perfect also.
Okay, so you have one more lecture that is scheduled on 2:30.
Okay, all right. Thanks. I'll
Okay,
join.
so can we start on 2:30?
Yes, yes, yes.
Okay, at present, if any participants have any queries, you can ask questions.
Yeah, please
Then,
ask.
or 2-3 questions. Now, after 5 minutes, we will close.
Sir, I have a question. I am
Yeah,
professor in neurobiology and cognitive science. So when we compare the trillions of neuronal cells in our brain or all over the body, how can we apply the same system in data-wise perception?
No, it is not. First of all, it is not same. It is similar. Okay, we just took the intuition from the biological point of view. I did not say it is same.
Okay, so we have to apply the same system for all type of neuronals. Even whatever millions or trillions of cells, we have to apply the same system to all type of cells.
See, billions and trillions of neurons, first of all, may
Network.
not be there in case of artificial neurons, neural networks. Okay, that is there in the biological neural networks.
Yeah.
Okay, 100 billions of neurons. I don't think it is trillion, but it is 100 billion, around 100 billions of neurons. Okay, that many neurons may not be there, but even if it is there, there is some logical structure of organizing them. It's not that every neuron is connected to every other neuron. There is layer by layer connection from one neuron sets to another neuron set, and we have also defined the connections. In the sense, there may be densely connected, there may be not densely connected. So there are various ways to define that. All that we'll see in the coming sessions.
Okay. Thank you.
Can I ask one question,
Yes.
Dr. Venkateshwara? So logistic regression is used only for binary classification. If we have more than two classes to divide the data into, then what do we do?
Yeah, there are ways to extend this basic binary classification technique for logistic regression to multi-class classification. Like there are various ways to extend that, one against all, one against one, and embedding method. There are different ways of extending this binary classification to the multi-class classification problem.
Okay, thank you.
Anyone else?
Hello, sir.
Yes, Ankit sir.
Sir, I want to ask a question regarding ensemble learning.
Yeah, tell me.
Sir, is it possible that we can incorporate the neural networks as multiple ensembles in the machine learning?
Yes, possible. That also in the, I think this improving deep neural networks, you have a concept called dropout. When you do that, you create a separate neural network every time when you do dropout. And finally you embed all these neural networks together to give the final results. So that is very much possible in case of neural network also, and which will be discussed also in the coming sessions.
Okay. And sir, I have another question, like why we need that dropout? I mean, actually, that I know, with the help of dropout, actually we are reducing the neural network size.
Yes.
Hello?
Yes, we're listening.
So why we need that?
You only told, no, to reduce the neural network size and also to avoid overfitting. To avoid overfitting problem.
Hello?
To avoid overfit problem, Ankit. Overfitting problem.
So I mean, I need to know why we need the dropout neural network.
That's what I'm answering, no, to avoid overfitting. I don't know whether he could listen to me or not. Krishna sir,
Okay.
could you?
Yes, yes. Yes,
Okay.
yes, I can hear. Any more questions?
Sir, I have a question.
Yes, Vishal sir.
Here we are taking inputs in binary form 1 or 0 only.
No. It can be any numerical.
Okay, so I am interested in mathematics of qubits as inputs.
Qubits.
Yeah, qubits, quantum computing approach.
Okay. So, I mean, you can represent that in some form of numerical form and you can pass it as input to this. Any numerical thing works here once you convert it. Even if you take
So
words,
for,
we convert into numerical form usually. One word one hot encoding, and we represent it in a numerical form and we pass it as input to this neural net.
so can you share some mathematics of qubit representation in ANN or some other deep learning approach
I
for
have to
some
look
classic?
at this. But then if you are, I mean, if the research is new in that area, you have to also see how to represent them, which is again a new research direction probably.
Okay, sir.
Yeah.
Thank you.
Any
more
other
questions?
doubts I can take?
Sir, whenever you apply example, the explanation, please apply the same with biological exam. That then it would be easy for us to recognize, understand, and to remember.
Okay, I'll try to do so.
Yeah, thank you.
Yeah.
Okay, so I think there is no question. So we will take break here. And thank you, Venkat sir, for a nice introduction of the deep learning with machine learning concepts. And we will listen you in the next lecture also. So for the participants, this is the lunch break. So we will assemble again on 2:30. Thank you.